Okay, so in this unit, we're going to show how to adjust for batches using SVA. So the first step is to actually estimate the surrogate variables. That's the name that SVA uses uh, to refer to what we have been calling batches. So that's the first step. Unlike Combat, we don't assume we know them. We estimate them from the data. We want to estimate them from the data without with taking into account the fact that we know that there's some variability explained by the outcome of interest. So we don't want to remove that part of it. So when you call SVA, you're going to feed it the data matrix from which we're going to estimate the surrogate variables, but you also feed it the model matrix that basically includes the outcome of interest. These have already been defined, these objects in the previous unit, and we're continuing on with the same R session. So just be aware of that. If you don't have those objects already created, you have to go back to the previous units to do that. So we're going to run this function, and it's going to estimate the surrogate variables. Take a little bit, and now it estimates them. It also decides how many to include. In this case, it decided to include 5. Now, once we're done with that, what we're going to do is we're going to basically fit a linear model that includes both the model matrix that was defined by the outcome of interest. We put that in X. That is a 24 by 2 matrix that has in the second column the outcome of interest, right? So it has male or female. And then it's going to include the surrogate variable columns estimated by SVA. So we create that matrix, and this one's going to have 7 columns. The first one is the intercept, the second one is the male-female difference column, and then the other ones are the surrogate variables. So now we can run lmfit just to fit this linear model for each gene. This is in Lima, so let's load up Lima. And it's very fast. There, it's done. So now to compute a t-statistic, we're just going to divide the estimated coefficient in the second column, which is the column related to the outcome of interest, by its estimated standard error, which is in this case you can very quickly do that calculation. It's the estimated population standard deviation for each gene, multiply by 2 because it's the difference, and then we have to divide this by the degrees of freedom, so that turns into a multiplication because we divide twice, and that gives us the t-test. Now we can compute p-values using the pt function. This gives us the degrees of freedom, so we can compute that. And now we have p-values, and now we can create a histogram and compare it to the one we saw before for the when the cases where we didn't adjust and when we adjusted with Combat. And now we have a flat, well, closer to flat histogram. It looks like what we expect. This is telling us there does not appear to be any differences between males and females, or very few, when we compare chromosome X and chromosome Y. So this makes me think that we have actually removed batch effects, and it was those batch effects that were creating or making us believe when we didn't adjust that there was a difference between males and females on the autosomal chromosomes. When we look at the Y chromosome, look at the p-values for that, we still see that there are differences. So we haven't thrown away the signal in this case, and that's exactly what SVA was built to do. Okay, now in closing, I want to just remind you that things don't always work out this well. One of the reasons is that the number of surrogate variables that are estimated is it doesn't always work well. It estimates too few or too many. So that is something that you want to take into account. And we will have in another unit, we're going to show you some tricks that we use to try to help guide the choice of how many to include. In this case, we just let SVA pick it for us, but that, like as I said, doesn't always work out as well as it did for this particular example.